Now let's look at some more details at how those gases travel in the blood. So we just went over the gas exchange between the blood in the lungs and the blood in the cells. Now we're going to see what those gases do while they're in the blood. We'll look at carbon dioxide first. Carbon dioxide has 3 methods of travel in the blood. The first one is the majority of carbon dioxide. 70% of the carbon dioxide in your blood does that reaction that we've talked about before. It mixes with the water in your blood and it forms carbonic acid. This then dissociates and you get bicarbonate and hydrogen ion. And because you end with a hydrogen ion, you decrease your pH. The second way carbon dioxide travels in your blood is 23% of the carbon dioxide enters a red blood cell. And if you remember back to chapter 18 when we talked about hemoglobin, we said that carbon dioxide binds to the globin part of it. So that's what 23% of the carbon dioxide does. Then the remaining 7% just dissolves in the plasma in your blood. It doesn't bind to anything, it doesn't react with anything, it just hangs out in the blood plasma. Then if we look at oxygen, oxygen has 2 ways it travels in the blood. Oxygen has a low solubility. This means that it does not like to mix with water. And we know that blood is mostly water. So 98% of the oxygen in your blood is in your hemoglobin. And it binds to the iron in hemoglobin. The other 2% will dissolve in plasma. So it's a low solubility, which means it doesn't like to dissolve in water, but it's not no solubility. So you do have 2% mixes with the water, but the other 98% rides on the hemoglobin. Then I want to explain what oxygen saturation is. So this is a common measurement that's taken, and we have those little meters in class that you've put on your finger before and you've seen your oxygen saturation. This is telling us what percentage of hemoglobins are carrying an oxygen, and this is in arterial blood. Okay, normal is 98%. Let's think of hemoglobin like a train. You have a train with 100 cars. This train flows through your lungs. as it does, you load oxygen cargo onto the train. In a normal person, you will get oxygen onto 98 of the cars. And 2 of the cars will slip by you without getting any oxygen onto them. This would be a 98% O2 saturation. "98% of your hemoglobins are carrying oxygen in your arterial blood. This is what is being taken out to your cells." Once that blood gets out to your cells, you give the oxygen to your cells. So this blood goes through your systemic capillaries, and it gives oxygen to your cells. Now, it doesn't give all of the oxygen to your cells. Once the blood has gone through the capillary and it's heading back to the heart, so now we have the venous blood. After the capillary is still typically about 70% saturated. So that means that you have 100 train cars, you have 98 of them have oxygen, you go through the capillary, and as you do, you'll say that 28 give their oxygen to a cell. Now you have your venous blood, where 70 still have their oxygen. So that's what's happening in a normal, healthy adult at rest. But when you exercise or you have a fever or something else going on in your body, you need more oxygen. So this 70 that you still have is called your oxygen reserve. You never want to just give away all of the oxygen and have your blood be empty of oxygen. You always keep a cushion or a backup. So the oxygen reserve is that 70% oxygen saturation in your veins. You can use some of that when you need it. So this picture is showing how you get that oxygen reserve. So getting the oxygen reserve would be that more of the hemoglobins give oxygen to your cells. So you're going to get more oxygen going to your cells, and it means that you're going to have a lower venous O2 saturation. So maybe instead of 28 of the train's cars giving their oxygen to the cells, maybe it'll be 38. There's 3 main ways that the body can induce the hemoglobins to give up more oxygen. And remember, this tends to happen when you're active. Because when you're active, you need more ATP, which means you need more oxygen. Okay, the first one Think about the second law of thermodynamics. If you forgot that, look back at page 73 in your book. When you exercise, you produce heat. And that heat stimulates more of the hemoglobins to let go of their oxygen. The next two we can lump together. Active cells make more waste. And that waste products stimulates the hemoglobin to release oxygen. The third one is carbon dioxide. Active cells make more carbon dioxide. And remember, 23% of your carbon dioxide binds to the globin. So right here is the globin. That's where you would have carbon dioxide. So if it's always going to be 23% that binds the globin, if you make more carbon dioxide, more of it will bind the globin. And this has the effect of kicking the oxygen out. Hemoglobin can hold either oxygen or carbon dioxide, but not both at the same time. So if carbon dioxide goes in, oxygen gets kicked out. Okay, so there is the oxygen and carbon dioxide, mainly the oxygen, in your blood as it's leaving your lungs and as it's leaving your cells, and how your cells can get more oxygen when they need it. Let's think a little more about this idea of oxygen saturation. I said that 98% is normal. If you wanted to get 100%, you would have to lock yourself in a hyperbaric chamber. The level of oxygen saturation in your blood is controlled by air pressure. This 98% is normal. That is at sea level. Okay, as you go up, like if you were to go up in a mountain, there's less oxygen. So at high altitude, there is less oxygen. The air is thin. And so if you go up at high altitude, you will have a lower oxygen saturation. This is why people get altitude sickness. If you go hiking in the mountains and your body's not used to it, if you're just there on vacation, you can get altitude sickness. Here's a chart that shows the percent oxygen saturation at different partial pressures of oxygen. So we start off here is sea level. As you go up in altitude, the partial pressure of oxygen goes down. And so your blood oxygen saturation would go down. Say you're somewhere where the partial pressure of oxygen is only 60 instead of 105, you would only be able to obtain a 90% O2 saturation. So the main idea here is that air pressure controls your oxygen saturation. At sea level, 98% is normal. If you wanted to get 100%, you would have to go into a hyperbaric chamber. And you would have to triple the air pressure. Then if we think about carbon dioxide, the level of carbon dioxide is controlled by how much you breathe. So this is what we were talking about before with your medulla oblongata controls your breathing rate and depth. And you have your autonomic nervous system. You can dilate or constrict your airways. So these things, your rate and depth of breathing and the diameter of your airways, this controls your carbon dioxide level. This is why you breathe slow and shallow when you're resting, why you breathe deep and heavy and dilate your airways when you're active. Okay, so let's look at a scenario. We have Sheldon here, and Sheldon is hyperventilating. This means he is breathing too much. If he's breathing too much, he is losing more carbon dioxide than his cells are making. This means he has hypocapnia, which means low blood carbon dioxide. So if his blood carbon dioxide is low, that means his pH is too high. So the paper bag helps with this. The paper bag will trap that CO2 that you are losing. And then it will allow you to inhale it back in. And this will then stabilize your carbon dioxide and pH. So the main idea here is that air pressure controls your oxygen level and how much you breathe controls your carbon dioxide level.